All right, Kane, in this short presentation, I want to give you a little bit of motivation for why we even care about the flux form of the integral. We've talked about the circulation form already, but what about the flux form of the line integral? Okay, now we said in a previous pencast or presentation how to get from this side to this side. That's one thing. But what's the physical interpretation of this? Okay, well, let's do this. Let's consider like you've got a thin sheet of water or some kind of fluid, maybe, okay, is moving across the XY plane. Okay, and an example of that we've used in class before. Maybe you think about like it's really raining hard, and the water that's driving down or flowing down the driveway, for example, like it's going down in like sheets of water. Okay, so something like that, but it's thin enough that we can consider it to be two-dimensional. All right, so we've got this two-dimensional moving fluid. And we drop this curve in it like this. We'll say positively oriented that way, okay? And at every point inside the fluid, we have a vector field that gives the velocity of any particle moving in that fluid, okay? So our velocity field, our force field, or rather is a velocity field, our vector field, excuse me, is a velocity field. And at every point inside the fluid, the vector that you see represented at each point gives the velocity of a fluid at that point, okay? And what we want to know, gang, is this. What's the net amount of fluid that passes across this curve C, right? So the fluid is moving inside of it, and is moving out of it. What's the net amount? Well, to answer that question, this is what we do, okay? Also, let me make a note here. This is our vector field F, okay? Okay, let's consider this. Consider a small piece of the curve, like maybe this little arc right here. We'll call that little piece of the arc ds, like we have in previous classes, like the length of a curve. Okay, so arc length, okay? What's the amount of fluid that passes through that little arc? Well, maybe that looks like this. Okay, so that's the amount of fluid that passes through that little arc. And it looks like a rectangle. It's not a perfect rectangle, right? Because the bottom, the base right there is a little bit of a curve, but it's small enough that we could consider it to be a rectangle. And so the amount of fluid that passes through that little arc is simply the area of that little blue rectangle, okay? Now to find that area, we use the vectors to do it, okay? So consider this. Let's say that maybe this right here is one of the vectors from the field. Okay, and let's take another vector here. Let's call that vector normal n. Okay, so I was a little bit careless there, but think of that vector n, gang, as being perpendicular to the curve. Okay, so we call it a normal vector. And I put that little hat over it to make it a unit vector so that its length is 1 just for convenience. Okay, so to find the area of this little blue region right here, I need the length of it and the width of it. The width of it I've got, that's ds, okay? But I need the length of it to get the area of this rectangle. And I can do that if I project F onto N, just like that, all right? Let's make that a green vector. I don't know if you could see that in the presentation, and the length of that vector which we recall that's the projection, right? That's the projection of F onto N. The length of that green vector is simply this. Okay, assuming the angle of theta between those two vectors looks like that. Okay, so let's see. The area of the fluid crossing the arc length element is equal to that expression. And why is that, gang? Because that gives me the height of the blue rectangle. See that when I project the vector F onto N, the length of that green vector will give me the height of the blue rectangle. Okay, well, here's that height. And if I multiply the height by the base, then I'll have this. Okay, so that's the area of that blue rectangle. Now watch this. I'm going to multiply this by a clever expression of 1. What do you think of my clever expression of 1? See that? Right? The magnitude of the unit vector is 1. So I haven't changed anything other than the appearance. But we also know from our previous work, don't we, that that is the very definition of dot product. Okay, so what's the total amount of fluid or the net amount of fluid that's crossing that curve? Well, we would simply add up the amount that's passing through, the net amount now, passing through each one of these little arcs. And we imagine the curve C is made up of an infinite amount of the, you know where this is going, right? It's an old story. It's an old story. So the total flux of the fluid through and across this curve is found by summing up all of those elements. Okay, and that's the reason we have this integral here. That's what this is for.